to today's topic. Of course, it's more in the direction of electric transportations and the fast charging solution. Today, I would like to, give the whole presentations under six main categories. First, I would like to touch upon why electric vehicles are so important in recent days. Why many governments are pushing their investment in this directions. Of course, we will see what is the key driver for this, and we will also look at the market overview of CAV. Obviously, many of them would have talked about electric car, wherein here I would like to focus more in the direction of CAV, which is generally, defined as commercial constructions and agriculture vehicle. So I will also give you some use case. This would be quite interesting to know, what kind of a charging solution is really needed for this kind of an applications. And then once the use case is clear, then the very important is before we go into an charging solutions are, the main drivetrain solutions. The application requirement is quite important to work around the power electronics circuits. Then I will also give a detailed informations about the fast charging trends, and then what are all the different topologies which is being used in this fast charging solutions. And I will also touch upon a few topics which is related to why the reliability is so important for this kind of an applications, and moreover how efficiency is going to play a big role in this industry. And finally, of course, how the near future would be shaping up. So this is also quite, interesting inputs. With these introductions, let me get into the uh, the first section, like mega trends and the key driver. If you look at from the mega trends perspective, I think everyone aware of this climate change and then scarce of resources. I think this is the big push, which is forcing the governments as well the industry to think in different directions, in a way of sustainable energy generation, sustainable energy consumptions. So, and if you look at the Paris Agreement, of course, most of the countries have signed that we would be keeping the global warming temperature below, initially it started with 2 degrees Celsius, and then now further the target being reduced to 1.5 degrees Celsius. It means a lot of changes needs to be happen from the energy generation till the energy consumption value chain. The another important the changes or the mega trends we see is like demographic and social change. Of course, today we have a populations of close to 7.1 billion, and then by 2025 it will be adding up another one more billion in this planet. Not only that, because of the medical advancement, the average life of the human being is also increasing. On the other side, because of fertility rate, the young population is also getting reduced, and down the line of 20 years, more and more, the average age would be going up. This is putting another, challenges from many aspects. One is like workforce challenges in the direction of workforce, challenges in the direction of entrepreneurs, challenging challenges in the direction of even running the health system. So naturally we can expect more and more people would be migrating, to different locations, and that is where the urbanizations would be quite prominent for the job reasons. Many of them goes into new cities, so the transportation is also going to increase. Then finally, in this corona period, we also have clearly understood that the digital transformation, which we were talking, but we can clearly see this is changing the whole culture of the communications, whole culture of the working atmosphere. So that is why this clearly tells us the power market could be moving in more in the direction of renewable energy. By this way, the CO2 emissions could be cut down, and the efficient power consumptions. So this is where the high efficient machine is needed. Either it could be used in the home appliances, or it could be used in the industry arena. So that is where efficiency is going to play a big role. On the other side, one third of the CO2 contribution, which is coming from the transportation sectors, and that is where like electric mobility is the clear directions to cut down the CO2 emissions. And moreover, if you look at even in the five metropolitan cities are under the top 30 list in the global polluted cities. So that is where there is no other option. We need to go in the direction of e-mobility to reduce the CO2 reductions. Otherwise, this subsequently bring a lot of other health issues, topics, and so on. So today we are going to more focus on e-mobility. Yeah, the good part is definitely the electric vehicle is not that new. If you know, the very first electric tractor being introduced in Russia in the year 1920, which is way back 100 years ago. And here it is a completely like this is not a battery driven agriculture vehicle. This is the electrical power supply was supplied with wire. I think you can see on the top of the tractor there is a kind of an a roller or a drum. Sorry, in this the cables being supplied for the electrical power. And recently, Terex, 3319 was the largest electrical vehicle. Of course, this is a kind of an diesel-powered generator, and then each wheel is having a bigger electrical motor. This has been driven out of diesel power. So this is also one kind of an electrical vehicle which we see in the market. But why now? We are talking hugely or heavily, looking at electric vehicle being the important directions. Since the main important issue as of today is the pollution, and if you look at the EU alone, the CO2 emission coming out of transportations, mainly it constitutes of road, aviations, and shipping. Roughly, one third of the pollution is coming out of the transportations, and in particular 72% 72% of uh, the contribution which is coming out of road transport. So that is where recently EU also estimates that roughly like one fourth of its pollutions is coming out of heavy duty vehicles like trucks, buses, and construction machineries. So this is the main reason electrifications in this kind of an vehicle is a must to reduce the pollution, mainly in the city areas. In this direction, the many governments are working with a very strict norms. If you look at, there are different regulations coming out from different regions of the world. The very first, the Europe region just had passed, the emission standards for the trucks, and the vision is quite clear. They need to cut down the emission by 15% by 2025 and 30% by 2030. And the scale is in comparison with 2019 emissions. So there is a clear trend that the emission has to be brought it down, and there is a clear roadmap how the emission could be brought it down. And if you look at, even US is also showing no lot of interest in this direction. Already the environmental protection agency has launched a cleaner trucks initiative, and they are going to update the nitrogen oxide standards for a heavy duty truck. So this also clearly says, the two part of developed countries are going in this direction. And not only that, if you look at the AP region, even in Asia as well, the Greater China is, taking a big lead in the direction of implementing the sixth, fuel standards. Out of this initiative, OEM also have to, prepare for a zero emission zones in urban areas. If you look at even in Germany and then few other European, cities, already they have kind of an banned um, the diesel cars and then diesel trucks into the city areas. And this is where, and whether the previous regulations or norms or guideline which has been set by the government to be met or not, the OEM has to meet, zero emission zones in urban areas. So this clearly says the market is going in the direction of electrical mobility. So here I would like to give you, what exactly the CAV market is, like commercial, constructions, agriculture vehicles. If you look at these vehicles are mostly used in a commercial arena, so that is reason it's termed as in commercial vehicles. Commercial vehicles could be trucks, it could be in buses, it could be used in public transportations, or by the institutions, or by the schools, colleges. And moreover for the industry purpose as well. And there are vehicles which is also being used in construction, that is being clustered under the construction vehicle category. And the vehicle which is used in the agriculture, this is also clustered into an agriculture vehicles. But it's clear that the mega trends in this area is fuel efficiency. That's quite straightforward, because as the regulation clearly says, we need to cut down the CO2 emission. If you compare this with the Indian standard, it's quite clear. We were at BS4, and then now BS6 being introduced, and moving forward, further much more stringent laws will be implemented. This clearly says the fuel efficiency is a clear roadmap to address this CO2 emission topics. So that is where we need to have a kind of an electrifications, mainly on the powertrain, not only on the powertrain. We also have to improve or bring the electrifications in the side loads, mainly like either it could be an heater element, or either could be an AC, or onboard, DC-DC stage. So everywhere the electrifications is going to happen. And on the other side, safety and then advanced drive assistance system, this is also a kind of an clear trends. It means you need to have an enhanced emergency braking. Then more and more we see the automation is also happening in this direction. So if the full automation needs to be done, means a lot of the big data has to be handled at a real time. This is also going to be a big mega trend which we see in this market. Then the connectivity, this is another big area, wherein today we will focus more in the direction of fuel efficiency and then zero emissions. You can see the clearly the industry is getting ready for this move. Obviously, there are a few models already being launched, but there are different technologies people are working around. You can see the first electric Volvo trucks, which has already been launched in the market around 2019, and this is mainly for used to deliver the goods for the customers. And there are many other portfolios like buses, electric buses. Not only electric buses, there are hydrogen buses also in the market. I will also touch upon like why hydrogen also will play a significant role in these directions. But one good part is like the electric vehicle is not new today. It's like 100-year-old story, and we can also clearly see the industry is gearing up, and then many electrical tracks is uh, launched in the market. This also clearly says industry is getting ready for this move. You'll see what are the different CAV use cases. The very first use case is like city delivery vehicles. Of course, if you look at a city, naturally in a certain area, accessibility is really a difficult. That is where today we see a smaller trucks which is being used for delivery purpose, and more because of the online shopping, the city delivery vehicle traffic is definitely going to grow. If you look at the use case of this city delivery vehicles, of course, many delivery service, they would be setting up warehouses in the city outer area. So the trucks will be coming and then dumping the loads into the warehouses, and then from there the goods will be delivered via this small delivery trucks or delivery vans, you can call it. So this, if you make it as an kind of an hybrid or make it as an electric vehicle, so this is one of the clear way to address the zero emission zone, mainly in the urban areas. Already there are plenty of models which has been launched and then which has been used since 3 to 4 years. We see there are huge number of this kind of delivery vehicles being used in China in particular. If you look at the use cases, obviously this van will be moving around city not more than a 50-kilometer circle. So that is where even if this city delivery vehicles having a range of 100 kilometer is good enough, and they have a multiple shift during break time, they can also easily charge. Then every shifts could be not less than 45 minutes, so that's good enough. They can easily charge additional 20 to 60 kilometer mileage using slow charges as well. Then the next use case, if you see the commercial vehicle, so this commercial vehicles, one use case would be a public transportations. Of course, for the public transportations, we need a different kind of infrastructures. I will also like take you through like why this public transportation needs a different kind of infrastructures. But if you look at a commercial vehicle use case for the point-to-point service, mainly this kind of a service being used in institutions or in the industries. Generally, it starts with a point A and then it goes to a point B. So again, the major use case here as well, it's not more than a 50 kilometer. That's a reason like in general, 100 kilometer range is good enough, since it starts from a point A and then pick up all the way the either students or the people who go to the industries. Then it goes to the industry and then it is being parked till in the evening. So this time is good enough to recharge the battery, and then once it starts from point B to A, again overnight this is going to stay at a point A. So that's the reason, like during the night, the vehicle is parked mostly in the depot, and then it can be connected to the charger. Rather, a low power charger is good enough, because the waiting time is more than a kind of in 3 hours. And then in this conditions, naturally, a low power charger is good enough to have a full charge. Yeah, and then the important aspects, if you look at naturally, you can charge this during low peak hours, mainly during the night time. If in the night time, if you are charging, literally you can charge the bus with almost kind of an lesser cost. Sometimes potentially they can also even get negative. So that's the reason here the charging options, mainly AC charging, is good enough, since your waiting period is significantly higher. That's the reason, like either a level 1 or level 2 AC charger is good enough. Or some case you can also use a wireless, but I will let you to know why, like what are all the other shortfalls of wireless charging, because you need to create an infrastructure for this wireless charging. So that's again one of the complications. The other complications would be it is the power is transferred over an air gap, and if any uh, the foreign bodies, if it is placed on the transmitter pad, then again this is another safety concerns. This has to be looked at, but in general, like the AC charging is good enough for this kind of an applications or this kind of an use case. So for example, if the same electric bus, if it is used for an public transportations, which is naturally, it goes all the way to, within the cities. And even in this cases, the city radius would not be more than a 50 kilometer, but here the shifts is not that big as compared to what we see the use case in the previous one. So that's the reason here in the every bus stop, if the bus is getting recharged at least for an addition of 20 to 60 kilometer, then it would be nice. It gives an additional mileage to it. So in this case, the bus might be stopping in the bus stop not more than 1 to 5 minutes. That's a reason, like you need to have a kind of a fast charger. So here you need to develop a different infrastructure as far as charging is concerned. Again, here the charging options could be like level 3, which is a high power charger. Mainly this is a DC charging, and with this you can easily charge the bus probably in 5 minutes, 50% or even sometimes even 60%. If this is the case, then you have to go for an pretty high power charger to charge the buses pretty fast. So we could see from the two use cases, you need to have the both AC charger as well the DC charger. Again, it's depends upon the use case. But how this kind of an public transportations could be charged? One of the way could be, because here it's quite difficult. The bus driver cannot get down from the bus and then connect the charging port into the bus. So that's the reason, like if it could be done with the pantographs, then it is much easier. And even we see there are underbody charging connectors is also getting into the usage. So generally, instead of on the roof, so they place it on the floor. So it has got a solid metal surface, wherein the top one you can see, this is the one which is coming from the bus. So then once this is getting aligned, then the charging is taking place. This is more a kind of an automized kind of an process. Cool. As I mentioned, not only this is an kind of one of the use case. The third use case is like the delivery vehicles. Particularly, this is mainly coming out of an online shopping. So there are a lot of traffics in the city is mainly caused by the delivery vehicles. Here too, the reduction of emission is achieved mainly by replacing the combustion engine into an electric or hybrid electric. Mostly, we also see the battery voltage and power levels. Generally, it's on the lower side since the overall weight and then the distance it needs to travel is significantly reduced. That's the reason, like smaller battery voltages and then smaller power is good enough to carry such a loads. Now let me just, so far we have gone through, what are all the use cases. From these use cases, we clearly know what kind of an charging options is needed. And then with this knowledge, we just step into an applications requirements. If you look at any bus, if we are replacing the combustion engine with an electric motor, so naturally, the drivetrain has to be electrified. So it means it's pretty simple. As of course, you need to have a motor and then gear sets, which is driving the wheel. So this is the main part of any electric bus you can imagine. Not only that, there are other area which need to be optimized or which need to be electrified. Otherwise this electrification may not be an optimized solutions. And if you want to increase the range, naturally the other circuits which is also taking a power from the battery, so it has to be optimized. Otherwise you may not get the proper range from the battery. So that's the reason there are a lot of electrifications has to happen, mainly in the direction of air conditioning, because air conditions runs 24 bar 7 if the bus is running for 24 bar 7. And on the other side, as of course, battery management is quite important. The reason is every manufacturer may not use the same kind of an batteries or same kind of an voltages. So that's the reason BMS is quite important, since this is the only communication platform between the bus and the charger. This is going to be a big topic as far as battery management is concerned. On the other side, yes, of course, you also need to provide an onboard charger. As we have seen, there are multiple use cases. So naturally, the bus manufacturers cannot make buses specifically for public transportations and then specifically for um, for the private users or commercial users. So in this case, naturally, they have to provide an onboard charger. It means the onboard charger has to be as small as from the weight as well from the size. And there are a lot of semiconductors which is needed. For example, the electrifications already we see in a combustion engine as well, like power steering, which is again a motorized steering, and a motorized braking, like electrical braking is also kind of an options which is getting popular. So it's quite clear there are a lot of challenges when you move from when you are changing a combustion engine into an electric motor. So holistic approach has to be taken place. Then only we can come out with a completely optimized, electrified vehicle. With this, let me give you like a brief idea about the overall block diagram, how it looks like. If you take the drivetrain alone, so naturally the drivetrain is quite simple. There is a motor. This motor has to be driven by power electronics. First, let me focus on an electric buses. Of course, naturally the electric buses, which has the main power supply is coming from the high voltage battery. The voltage could be ranging between 400 to 650 volts, and even in near future this may also go up to like 1000 volts. But these days we see the battery is in the range of 400 to 650 volts. So from this battery, this input is given to the power stage, wherein this is a simple two-level three-phase inverter. This has to drive either a PMSM machines or an induction machines. Of course, on the other side, if you look at there are onboard supply is also needed. So it means the high voltage has to be converted to a low voltage. This low voltage level could be like either a 12 volts or a 24 volts. So mainly this is needed. There are many electronics which is placed on the bus. So this electronics will be running with a rail of like either a 12 volts or 24 volts. So this power supply also has to be derived out of this high voltage battery. Then we also need the additional power managements, like for example, to drive the gate driver we may need a plus 15 volts and then minus 15 volts. And then on the other side, for the microcontrollers, naturally today you need either a 2.5 or 3.3 volts. So there are a lot of further low voltage need to be generated to derive the auxiliary power circuits. Yeah, with this, again, the microcontroller not only does the PWM operations to control the motor, of course, the input has to come from the human machine interface. So this is also quite important, and moreover, this also has to give the status indications how it's overall it's running. So this is the mainly, the block diagram for an electric drivetrain, mainly which is used in an electric buses or in a few tracks. But if you look at as the size goes bigger and bigger, then naturally we cannot purely depend on the high voltage battery alone. Then mainly for the construction vehicles and then mainly for an agriculture vehicle, the power requirement is pretty high. And here mostly the electrifications would happen like a diesel electric system. So the below there is an additional kind of an two block sets which is representing mainly the mining and construction vehicle block diagram. If you look at yes, of course, the it is primarily run by a diesel generator, and then this diesel generator provide the primary source of power. But naturally the advantages of converting the combustion engine into a motor, this itself brings a lot of optimizations on the efficiency front, and rest of the block diagram would remains as it is. Cool. Then let me also give a detailed idea about how the overall the specifications would look like. So generally, if you're talking about the electric bus, so we can categorize the electric bus by with its different length. So it starts from 9 meter and then goes as high as an 18 meter. So that's the reason depends upon the size of the bus. Then you need to have a different power rating. So the power rating of the motor can vary from 100 kilowatt and as it may go as high as 250 kilowatt. In some cases, one bus might be having two motors, like both rear and then front kind of an drive. And then some buses have only the rear wheel kind of an drive. So it's again depends like what kind of a load this has to pull in, and then what is the size of the bus. But in general, if you look at the motor which is predominantly used is either a PMSM machine or the induction motor. Mainly for example, this is for an electric bus. If we talk about the constructions and then agriculture, their reluctance motors are quite popular. And if you look at the battery voltage, yes, of course, as I mentioned, the battery voltage ranges from 400 to 650 volts. And the battery type, predominantly, it's a lithium ion battery. And if you look at charging charger ratings and the charger type, as I mentioned, we have to rely on both AC charger and DC fast charging. Since when we talk about the bus, of course, L1 AC charger is not a viable solution. That's the reason they go for an L2 charger, which is a three-phase charging options. As high as we could see, like a 50 kilowatt AC charger, but this 50 kilowatt used to be placed on the wall mount, not on board. But generally, for the onboard, we see it's something less than 20 kilowatt. Of course, if it is used in the public transportations, then the DC fast charging option is also needed. So in this cases, the charger typically ranges between like 50 kilowatt and then goes as high as 350 kilowatt. So mainly for fast charging, you can term it as 350 kilowatt, wherein the slow charging or AC charger, the power rating, the maximum is like 50 kilowatt. Then when you look at what kind of an converter is needed for this kind of an electric bus application. So generally for the main propulsions, of course, we need a two-level inverter because this is good enough. Generally, the motor has a certain, operational limits. I will go through that operational limits also in the upcoming slides. That will tells you this kind of an motors. Anyhow, you cannot switch it beyond 10 kilohertz. The sweet spot could be less than 4 kilohertz. This is where you can operate this kind of an 100 to 250 kilowatt power level. So that's the reason, like today to the 1200 volts silicon chipsets is good enough to handle, or it is optimized to handle in a two-level topology. Yeah, I have talked about more on the other auxiliary requirements. And if you look at the converter requirements outside the vehicle, mostly it's an DC fast charger. Of course, the main end usage would be the public transportations. So this gives further, a detailed view about what kind of an, the detailed application requirements from the motor perspective. If you look at this, everything we have talked about it. The drivetrain, the power ranges from like 100 kilowatt goes up to like 300 kilowatt. And the auxiliaries, it may start from less than 1 kilowatt and goes up to like 10 kilowatt. The onboard chargers is, of course, it is up to 50 kilowatt we see in the market. So generally the switching frequencies for this kind of an power level is less than 10 kilohertz. Naturally, for example, the auxiliaries is, of course, you have a flexibility. You can switch it as fast as possible to reduce the overall size, and then also you can optimize the overall efficiency. Since this is running 24 bar 7 hour, the full operation still the bus is running. So that is where you need to optimize the auxiliary circuits for this kind of an applications. Otherwise the battery will drain pretty fast, and you may not get the range what it is expected. But in general, the motor used to be switched at a low frequency, because this limitation is coming from, one is coming from the DVDT. This is the standards limitations. They mainly the motor cable has a limitations which is less than 5 kb per microsecond. Since predominantly this is driven out of the drive industry, but naturally here the cables are not pretty long, because in recent days we also see this kind of an inverters being integrated into the motor. So this gives a little more flexibility to go beyond less than 5 kb per microseconds. The discussions is on like up to like 10 kb per microseconds also we could see in the market, because the specification is quite important. The reason is this is going to decide what kind of an semiconductor technology could be utilized. For example, if you are using a silicon, if you want to use a silicon carbide technology over here, 5 kV microsecond, which is something like you have to slow down the silicon carbide MOSFETs. If you slow down, naturally you cannot exploit the full potential of the silicon carbide components. So that's the reason mainly for the drivetrain, the solutions is mostly in the IGBT side. Then what kind of an short circuit capability, this kind of an application demand is a minimum of 8 microseconds, is of course, if any cable short circuit happens, then the IGBTs or any other semiconductor chipsets which is used has to handle 8 microseconds short circuit current. And by this time, the short circuit protection circuit will sense and then protect the overall circuits. On the other side, the very important specification is, this also have to start with a 0 hertz. Mainly, um, if the bus is in the stop and it has a heavy load, and then it need to provide a torque at a 0 hertz. One is that, and then the other is like, even when it goes to an uphill, or it's starting off a hole, or claiming the payments. So this is where the 0 hertz kind of an operation is quite important. Naturally, this is not a big deal for any motor, but it is a question that, yes, this is a quite big deal for semiconductors as well from the battery. From this, we can easily derive out of this the overload capability, because during the start-stop operations, or with locked rotor conditions, the starting current as go as high as like between 150% to 200%. I will also give you a details about like this kind of a cyclic load. What are all the difficulties, or what are all the challenges on the semiconductor front? For example, yes, of course, uh, this is an electric bus. Of course, this is not a battery electric bus, but the same phenomenon could be applied for the battery electric bus, because only here the source of electricity is coming from on the rooftop cable. But the electric drivetrain is quite similar, even whether you use a battery electric vehicle or a pure electric vehicle. So if you look at here, the nominal voltage generally it is of 600 volts, typically 600 volts DC. And this kind of an city ride buses, typically we can see the station distance would be less than a minute. And here the cooling method is a liquid cooling, and you can expect like more than 60 start and stop operations in 1 hour. And every day this bus could run nearly 16 hours of operations, and in a year it's like 300 days of operations. If you look at this is the mission profile of this particular use case. As I mentioned, during start stop operations at a stalled condition, or at a locked rotor condition, then you may end up in having initial starting inrush current. Then once the vehicle starts moving and it generates the inertia, then the load on the motor will comes down. So this is how the profile looks like every start and then stop operation. You can see like the ripple on the semiconductor side. So the green curve, which represents the temperature ripples of the diode, and the red is the temperature ripple of IGBT. This is quite important from the semiconductor perspective, since every delta T is kind of an life-killing activities which is happening at the semiconductor front. So finally, what will happen if you look at a semiconductor technologies, like you can imagine that the semiconductors is not only constitute of the semiconductor chipsets. Since this semiconductor chipsets has to be placed into an package, this package need to be use a certain joining technology. Like I will give you a brief idea. Like in today's scenario, we use a standard joining technology. What exactly the standard joining technology is? You have a silicon chipsets. You can use it for a silicon carbide as well. Then below the silicon chipsets, this silicon is placed on the DCB, which is direct copper bonded kind of an substrate. This provides an isolation basically. So then this kind of an modules can be placed onto the heatsink, so without any isolation. So any kind of an circuits could be placed on one single heatsink. So because since this kind of a module is completely isolated, to do so, naturally the silicon chipsets has to be joined on the DCB. Then further, this DCB has to be joined to the base plate. This everything has been done by standard chip soldering. And if you look at the top surface of the silicon chip is again using a bond wire constructions. Of course, you need to have a collector and emitter. So probably the top surface would be acting as kind of an emitter, and then the collector would be on the bottom side. So then by which there are terminals which is coming out. This is going to make the external connections. This is quite nice from the joining aspects, but every components or every materials which is used in this joining process is completely different. For example, the base plate is of copper material, and this is like the ceramics, and then the copper is bonded together. Then we have a silicon which is exactly like a glass or a crystal. So everyone has got a different thermal expansion behavior under different power cycling conditions. If you look at in the previous ripple chart, the chip is going to see the highest ripple, wherein the base plate is going to see the lowest temperature ripple. I think this is clearly evident. For example, this starts from somewhere like 35 degree, and then it goes as high as like 70 degree. So this is where the delta of somewhere close to like the 40 degrees the delta. But if you look at the chipsets like IGBT, again this starts from 35, but this goes as high as close to 90 degree. So again, you can imagine how big the delta is. And on the diode side, again, you look at how big the delta is. So this delta is going to stress. The big stress would be coming on the bond wire, since that expansion happens pretty fast because of the higher delta. And then if this the stress is quite significant, and it is happening for many a times in its lifetime, then how fast this kind of a ripple happens, then this will reduces the overall lifetime of the module. This is mainly contributing from the temperature ripple which is on the chipsets. And if you look at, there are also solder which is being used to connect the chips and the DCB. The chipsets, and once there is a void, it means there would be a kind of an poor heat transfer. Again, this further increases the delta T, and finally the module will fail. So it's pretty clear this kind of an applications demands a higher power cycling capability and a higher thermal cycling capability. That's the reason like the industry is already working on a kind of a different platform, wherein Infineon is working with the .xt joining technology. And this the chip is not solder, this is a sintered. It's like an silver paste, which is having an higher melting temperature compared to the normal lead free solder. So normal lead free solder, the melting temperatures could be somewhere between like 180 degree. It can go as high as like 220 degree Celsius, wherein this is silver material. Of course, this melting temperature is way high as 900 degrees centigrade. So that's the reason like this can handle huge stress. um, then We also use a diffusion soldering at the bottom. Again, this also brings a huge, stress handling capability. By this way, we could expand, the end of operation life area. For example, the red one is the number of failure, the power cycling capability. By this way, by using a .xt technology, we can easily lift off, the capability by 10 times, which means if a normal technology could deliver a lifetime of 2 years with a fixed power cycling curve, then with the .xt we can easily reach 20 years. So it's pretty quite natural that for this kind of an applications, the reliability is quite important, because you are carrying the passengers, and then meanwhile, if any failure means a reputation is getting spoiled on us, that, and then yes, it causes a big financial losses as well, the reputation. That's the reason, like, you also have to look at what is the application requirements, and then for the application requirements, how this power cycling demand could be met. Then you have to pick up, the right joining and then right chip technologies. Cool. What does it means finally? If you use a standard module, naturally in its lifetime, you have to change the module at least twice. But if you use a .xt, this kind of a new joining technology, the lifetime or the service time could be extended. Cool. Then let me also give some overview about how the silicon carbide could play a big role in this industry. Mainly, if you look at the main inverter, the potential for silicon carbide is yes, but the money which you are going to spend for a silicon carbide, is it paying off you or not? So this is where the question is, and then that's a reason, like, today this really not brings a significant value. The reason is being, as I mentioned, the switching operation has to be limited to 5 kV per microseconds. It means you have to literally slow down the silicon carbide MOSFET switching speed. So when you slow down naturally, this will increases the losses, and then the end benefits what you are going to get at that particular operation point. So naturally this is not coming to a kind of an win-win situation. So that's the reason today we don't see an opportunities, but there is a huge potential. For example, if this specifications could be removed, and then it is allowed that you can switch it a little more with a higher dv by dt, then so naturally this will bring a lot of space and weight savings. Not only that, further it will improve the efficiency of the inverter. Increased efficiency means, again, this will increase the range of the operation. But we clearly see the trend, the silicon carbide, which has been used in the auxiliary applications, because in the auxiliary circuits, naturally you need to have to provide the bigger space for the passengers to be seated, and you have a less space to accommodate all your power electronic stuffs. That's the reason, like, the auxiliary converters has to be smaller, and the weight also has to be very low. So that's the reason, like, you have to operate at a higher frequency. And on the other side, there's no limitations to operate this DC-DC or HVAC or onboard charger, so you can switch it at higher frequencies. So that's the reason, like, we clearly see silicon carbide is heavily used in this scenario. And moreover, all this auxiliary applications is taking power from the battery, and then whatever the percent of efficiency which you say, this finally going to save the energy cost. Cool. Then let me just get into the or different topologies, and then the application trends which we see in the charging solution. So far we have seen how the powertrain solutions would be, and then what are the requirements of the powertrain, mainly from the semiconductor side as well, because initially we started with on the motor side, and then afterwards we moved to what it translates into the semiconductor, since when we are designing and power converters, naturally we have to look at both the reliability, and then it also have to meet the requirements of the applications. On the other side, depends on the use case. There are different kind of and charging solutions need to be deployed. So now I will just take you through what are all the different, the requirements for the charging applications itself. But the same could be applicable for the electric car, or if you talk about electric bus, or if you talk about the constructions and then agriculture vehicle. Only the question is the power would be scaled up, and in this case the voltage is also getting scaled up. The commonality would be most of the the block level approach would remain similar. Good. So there are different charging solutions are possible. One is like an main harbor charging. This is mainly for the public transportations, where depot can install this kind of an harbor charging. So during the night time, every buses could be connected to the chargers, and then overnight charging is possible. In this case, both options are possible. Fast DC charging is also needed, and then the AC charging is also needed. Fast charging, for example, if a driver wants to take a break, then they just put the vehicle into the depot, and then they go for a break for minimum of 45 minutes, and under this short time kind of an duration, then naturally you may not need very ultra fast DC charging. A fast DC charging is good enough. On the other side, the destination charging, since the destination charging is like mainly, for example, beginning and end of route. I think what I explained about point to point service. So where you start from point A and then end up at point B, and then the rest time is quite significant. There you can easily charge your vehicles. This end applications could be either schools, colleges, and then the industries, or even a shopping mall. In that concern, you can look at it. Then there are kind of an opportunity charging. This is mainly coming from the public transportations, where for every bus stops, you can have this kind of an opportunity charging, either by using a pantograph as an options to connect your charger to the bus battery, or from the bottom you can also make a connection. So here fast DC charging is must. We also see like wireless charging is it's quite fancy stuff. Today the power is limited less than 10 kilowatt, and we also see in European countries, they have laid a dedicated corridor for the wireless charging. So, but the implementations in a mass side, it's quite difficult. But we clearly see the fast DC charging and then the AC charging is the clear-cut options to go. Now, let me give you a detailed, idea about what is the application aspects of this DC EV charging. If you look at battery charging, mainly it's a constant current applications. So typically, the thermal cycling requirements for this applications would ranges between 10,000 to 30,000 cycles per year, and the service lifetime is somewhere between 15 to 20 years of service lifetime. Here we see the ultra high power charging may go beyond 350 kilowatt, but generally for the fast charger it will be less than 350 kilowatt. But what is the challenges in going with higher than 350 kilowatt? naturally on the one side, because this is the cable which has to be plugged out from the charger, and then you have to plug in into your vehicle. So the cable has to be thinner. If the cable is so thick, then it's quite difficult to pull out and then plug in. So this going to bring huge challenges. That's the reason, with the existing voltage level, for example, 600 volts level, then the current would be way high. That's the reason, like, you have to go for a higher voltage category, like 1000 volts DC. Then only this higher charging is possible. Then you also need to have a liquid cooling for this cable, so otherwise you cannot make the cable thinner. Then in this directions, we also see a charge in, and CHAdeMO is mainly focusing on 1500 volt, the DC rail system with a current up to like 300 ampere, mainly for CAV applications. I can also touch upon, this is also not only the direction, there are other directions which is also getting shaping up, but we have to just wait and see in which direction the industry will move. But the good part is, the industry is started working on two different directions. Finally, mm, the manufacturing scale, and then the market is going to decide in which direction to move on. Here, if you look at the efficiency target is 98%, because you are selling the energy. So that's the reason the efficiency has to be on the higher side. Today, it is at 95%. It means the efficiency improvement is quite huge. And there is already discussions which is on in the European countries. Mainly today, you are paying the energy cost using AC meter, but on the other side, what the users or the customers are paying is they are also paying for the energy loss as well, because the power converter is before after the energy meter. So that's the reason you end up in paying whatever the losses which is happening on the power converter as well. So in European Union, this was a big discussion. Is of course how a customer could be penalized if someone is installing a poor quality charger or a poor efficient charger. Then now already there are a few players, they come out with an DC meter. So once the policy is derived out, probably in a year or a couple of years, the DC meter will be a standards in Europe region. Then yes, of course, if this comes into the picture, then there will be a more focus on the efficiency, since the charging park operator has to lose the money, whichever the loss which is happening. So that's the reason, like, they would be putting more focus on the efficiency targets. Then from the design aspect, if you see, naturally the EV charging goes in the direction of modularity. What exactly the modularity means? In the past, the 15 kilowatt is the standard, and they can use something like 10, they can stack it up to reach 150 kilowatt. And if you put a 20 racks, you can reach easily 300 kilowatt. So this is how today the design architecture would looks like. So generally this comes with a 19-inch rack with a 3U form factor. Now because of increasing in the DC charger rating, and increasing pressure on reducing the cost of the charging, now they go into a kind of an higher power charging, like each rack of 60 kilowatt. By this way, by just plugging in 5 times of 60 kilowatt, then you can reach a 300 kilowatt. Just see like how many number of units you can brought it down, and then with a smaller space you can place a 300 kilowatt. This also reduce the space which is needed. This is quite important from this direction. So From the design perspective, naturally it looks interesting, but what are all the challenges? See, in the past, you were, dissipating 300 kilowatt, even a 3% loss of, efficiency means roughly like 3 kilowatt per 100 kilowatt, and then 9 kilowatt losses you dissipating in this so much of area. Wherein if you are trying to shrink this by roughly one two-third of it, it means a huge challenges from the power dissipation side as well. That's the reason you need to go for an high efficient design. So this will naturally eliminate those challenges. But the question is how you can reach to this target level. Of course, by choosing an appropriate topology, you can improve the efficiency, but beyond some extent, you need to go for a silicon carbide component. By using a silicon carbide component, you can also, switch it at higher speed, and you can reduce the overall magnetics, by which you can shrink the size of the racks. One is that, and then on the other front, even if you are switching at a higher frequency, the silicon carbide, chipsets will the losses will be on the lower side compared to the silicon IGBTs. So that's clearly tells us, silicon carbide will be the future, mainly in the direction of electric vehicle charge. Cool. What are all the different standards which has been in practice? If you look at charging, this is mainly a standard which has been followed in US and then Europe Union. Here, they define in a different levels, like level 1 and level 2. This is an AC charger. Here it's like 1.4 kilowatt for level 1, and then level 2 it goes as high as 7.7 kilowatt. If you look at this is 240 volts. This is an kind of an single phase, uh, and the three phase options is also available. Wherein if you look at a fast DC charging, like the CCS 1000 volt standards, which allow you up to like 350 kilowatt, and in the near future, this is proposed, but it is not yet implemented. This is an 1500 volt with a 3000 ampere. You can go as high as 4.5 megawatt. Generally, this kind of an higher charging power is needed mainly for bigger trucks, and then the constructions, and the agriculture vehicles. CHAdeMO is of course, this is the standard coming out of China now. Chaoji, this is kind of a collaboration between Chinese and Japanese. Sorry, CHAdeMO is a standard which is coming out of Japan, and then GB is the standard coming out of China. And this has been getting harmonized. They are just formulating a common standard that will be called as an CHAoji. So in this case, what they try to do is like they can go up to like a 900 kilowatt power level, but here the voltage standard is totally different, because you can imagine 3000 ampere, how big the cable size would be. Here what they do is like they allow up to like 600 ampere, and they find it 900 kilowatt is good enough to meet even the future requirements as well. So India is of course, they have adapted GB by T as the standards. We have to just wait and see. Still, there is no clear rollout of the standards. So once the rollout is done, naturally, like then based on this, then the charger options which will be getting evolved. Good. This is more in the direction of standards, and this is more in the directions of what is happening in the applications, and what is driving for smaller footprint chargers. But now we dig more into how this could be realized from the power electronics side. So naturally, this is an isolated topology because isolation is the minimum standard which is need to met whenever you are charging any battery electric vehicles. But you get the power supply from the grid, so then you have to convert this AC into an DC. So this portion could be addressed in multiple way. First, let me just focus on AC/DC itself. If you look at AC/DC itself, if it is a less than 50 kilowatt design, so then they go for a VNR rectifier. Since the VNR rectifier, the advantage is pretty straightforward. Since the voltage across the switches will be much less, and then this also considered to be in a high efficient AC/DC topology. And this also offers the power factor corrections, and then the THD level also could be minimized going in the direction of VNR rectifier configuration. Yes, of course, the shortfall of this VNR rectifier would be bidirection is impossible. When you go for more than a 50 kilowatt design, naturally handling such a high power in a three-level topology is highly cumbersome. That's the reason active front end is the clear direction. So in this case, it's quite easily you can implement the bidirection features as well. If the power level goes beyond 100 kilowatt design, what you have to do is naturally you need to have your own transformer. If the power level is going beyond 100 kilowatt, then isolation is done at the input level. So then you can have a two secondary winding of star and then delta. By this, you can have a 30-degree phase shift, by which either connected in series or parallel, you can compensate the TST, and then you can also compensate the ripple component which is coming out of it. So generally, bridge rectifier configuration is good enough. Cool. Then it comes to an DC-DC section. So if on the AC/DC side, if you have an isolation, sometimes like for example, if the design is more than, or if any park is more than 100 kilowatt, then the isolation has already been taken care from the input itself. Then in this cases, non-isolated topology is also popular. By using a simple buck boost operations, you can also charge your vehicle without any isolation. But the question is, if the input doesn't has any isolation transformer, then naturally you have to go with an isolated topology, which is high frequency DC/DC stages needed. There are multiple topology which has been followed. The quite popular is an LLC and then phase shifted converter. But LLC and then phase shifted converter offers a great efficiency. But the shortfall of this LLC topology is if you need to have a wide voltage range. For example, if you take in India as an example, already there are cars which is available from 48 volts on road, and today they are talking about 200 and then 400 volts. Look at the charging requirements. So it has to charge even the car, or the electric rickshaw with a 48 volt, and as good as it has to charge the bus with 400 or even higher voltage. It means the voltage variations for any charger is quite big, and then this huge voltage variations cannot be handled by LLC or a phase shifted converter. That's the reason, like the dual active bridges could be one of the solution to address this wide range of voltage ranges. Cool. The other big problem from the standard itself, if you look at, this is the standard which is coming out from charging. So they also give 5 operational limit. One is like 920 volt with 150 ampere, which is roughly 94% of the power level. And then if you look at 800 volt, it's like 437.5 ampere. Then at 500 volt, 500 ampere is the limit. And then at 200 volt, 350 ampere is the limit. And then there is another limit, 200 volts, 150 ampere. See, if you look at, from all this, the power limitations, there are, large portions of the operating lifetime is spent at light to medium load, and the variations of this percent is also huge. So, optimizing the efficiency for the full range of operations is really an complicated challenges. And this also, have to look at, for example, at a lower voltage you need to have a higher current. So higher current, again, it constitute for an higher losses. On the other side, the higher voltage which lower current, again, this is other dimensions which has to be looked at. From the power electronic perspective, we have to look at what is the peak load, and then we have to, dimension all the power electronic components to the peak constraints. So it's very difficult to optimize the efficiency for the full range of operations. And today there is no clear standards for this efficiency, but a kind of an, what the standard which is being followed in computing power supplies, like 80 plus standard. This is going to be applied even for the charging applications as well. If this is the case, then the clear directions would be, the MOSFET behavior with the silicon carbide material could benefit a lot. For example, generally what we talk about is the DC bus voltage ranges from, 200
Video na? Sampai ke menu kok.
goes as high as like 600 volts. In this range,
Video
clearly,
apa tu na?
you can
Ha?
see
Video na?
the silicon
Video kau na?
carbide has taken a great edge on the total losses. And also the other interesting fact of the silicon carbide is, like, you can see the huge difference from the loss when it comes to the junction temperature
Apa ini?
operation. For example, like, the junction temperature, in most of the cases, it would be like for the peak load, it would be on the higher side, like 150. Under this case, just look at the IGBT. The losses is quite big comparatively. And even at a light load, you also get a better, efficiency compared to the IGBT solution. So on the other side, again, if you look at the current, so if you are going for an higher current, so naturally the silicon carbide takes, big edge on silicon solutions. From this, you can see, you can easily imagine any charger would having a different, output voltage levels. With this different output voltage levels, you can see clearly the silicon carbide is taking an edge on IGBT. And at a different load condition, different junction temperature is expected. Even and at a different junction temperature operation, silicon carbide takes a huge, lead in this direction as far as the losses is concerned. So from this, clearly it is evident for different load conditions. So if you need to achieve an optimized efficiency, for example, 98%, this is possible with only a silicon carbide. So it's clearly tells that, silicon carbide is the future, mainly in the direction of electric vehicle chargers. Good. One of the typical example what we see in the market is, like, in the past, mostly this is an, full bridge LLC topology. It is being designed with 650 volt silicon MOSFET. Yeah, super junction MOSFET. So there are two MOSFETs which is connected in series, or two stage of, full bridge LLC are connected in series. So you can look at the number of component counts. For example, on the primary side, you need an eight silicon MOSFETs, and then on the secondary side, you need eight silicon MOSFET. Total 16 number of components has to be mounted. Wherein if you convert this to a 1200 volt silicon carbide MOSFET, You can easily reduce the component count by half, by which either one way is you can increase the power density. On the other side, you can put another rack, and with the same size you can increase the power by 2 times. So this clearly tells this is the way to look around how you can easily shrink the size of the overall charger, and how you can improve the efficiency of this kind of a charger. Cool. Let me also give some idea about the wireless. Today we see the power range. It starts from 3.6 kilowatt and goes up to 11 kilowatt. Naturally, here the topology would be remains quite similar to what we see in the previous fast charging. Yes, of course, your grid is a three-phase. It has to be converted to DC. Then DC, a high frequency, needs to be generated, wherein below you have an induction coil. So so instead of the core based transformer, here you have a air core, kind of an air core, and this magnetic field being transferred to the other side of the core material. And again, you need a high frequency square wave to a DC conversions. This has to be done. It's a rectification. Then you need to have a DC-DC, since the voltage control is done in this DC-DC section. So almost if you look at the DC-DC stage, it is a quite a replication of what we see, what you see in the previous section. But the question is like the since it is more, the efficiency is the transfer of energy is more dependent on the air gap, and then this air gap is maintaining air gap is also one of the complicated topics today. We see the model are the proven model goes up to like 11 kilowatt. Beyond still, there are some research which is going on, but we don't clearly see a big market for the wireless power transfer, because of their poor efficiency. And again, every car manufacturers has their own coil design, and then this also reduces the performance, or the variations from the performance level varies with reference to different kind of and manufacturers. So there are different challenges, but of course this is also one of the possibilities the industry is looking into it. One key informations, like already the German had come out with an regulations that, for example, within 4.5 hours of operation time, the driver has to take a rest of 45 minutes minimum. This can be split into 15 plus 30 minutes. Because why I brought this topic is like there is no need to meet the ultra fast chargers, or there is no need to go in the direction of ultra fast chargers, since anyhow the driver has to take a rest of 45 minutes within 4.5 hours. Means in this 45 minutes, even if you charge, like for example, every electric vehicle could run a kilometer with a 1 kilowatt hour power, then even if you charge a 22 kilowatt within this 45 minutes of time period, that's good enough. It can give an additional range of 20 to 60 kilometers, though the city radius is not more than 50 kilometer in most of the cases. Then in this directions, if similar kind of regulations comes across a different country, then this itself takes care of kind of an stay with the DC fast charging, which is less than 350 kilowatt, or even slightly lesser than that power. This also comes pretty handy from the grid stability point of view as well, and this also gives a comfortable rest for the drivers as well. This is one, if it has been implemented across the world, then this also creates a big impact in the charging directions. On the other side, Just for you to think, like for example, this kind of an buses not only used in US. Yes, this is kind of an buses. It's also used in India, mainly for schools, colleges, and then again for industries. If you look at again, it's a point-to-point services. Like it starts from a depot and goes to the end destinations, and then finally go back to the depot. If you look at in general, like in US alone, there are 440,000 of school buses which is running on duty. And in this, you can consider like 100 consecutive days for an summer vacations, because these days the buses are not utilized, and there are nights and weekends also included in this 100 consecutive days out of 365 days. And if you consider a 220 kilowatt hour per bus, this means nearly almost like 100,000 megawatt, the storage capacity just sitting idle. So it's a question that all what you need to do is like if you make a bidirectional charging hardware, then this can be used for the grid stability purpose as well. So why this kind of a battery has to be just sitting idle, or in a way that anyhow you need to have an energy storage system in order to bring a grid stability when you connect so much of charges into the grid system. So instead of adding more batteries as a standalone unit, so there are already batteries which is running on the car, batteries which is running on the buses. Why don't you utilize this battery? So this vehicle to grid, this is already being a big talk in the industry, and then many of the manufacturers also thinking in this direction, to go and make kind of an bi-directional charging hardware. Good. There are other improvements also which we see. For example, so far, whatever we have discussed, the solution for the city transports. Suppose if you are looking at a city to city connectivity transportations, are goods in that case, goods has to carry from one harbor to the another city. So then it's a long distance which is needed. Again, long distance is challenges. One is that you need to have a bigger battery size to have a higher range of operation. One is that, and then other is even if you want to charge it on the highways, of course you need to set up a fast charging infrastructures. Instead, Japanese and even in that case, Germany also investing heavily on the hydrogen-based fuel cell concepts. But the question is, of course, this is a viable solution. We also see from the industry perspective, like for the heavy trucks, and then for bigger power trucks, instead of going in the direction of electric battery electric kind of and stuff, they can also go within fuel cell configurations, because we have all the infrastructure in place. Only the question is, instead of CNG, you can use that infrastructure for the hydrogen storage. So this is possible, but the good interesting part is, anyhow you need to have a high speed compressor, because the hydrogen has to be flow into the fuel cells, where you need a high speed compressors. And you also need a DC-DC stage, since the energy which is generated out of fuel cell is a DC. Then to drive the motor, of course, you need to have a DC-DC converter. Then you also need to have an kind of an onboard supplies. So the question is of course the power electronics content, or the power electronics is going to grow, and the semiconductor contents also parallelly it will grow. This also leverage further field for optimizing the efficiency of this overall power conversions. So naturally, automotive is the big industry where silicon carbide could leverage the full potential. Good. Now, I'm just coming to an end. Of course, we have covered a lot of topics. Why electric vehicle is so important in recent days, in order to control the CO2 emission, and then keep the global warming level below, 1.5 degree centigrade. This is really important. And of course, the highly populated cities need to move into an electric vehicle in order to reduce the pollutions. Otherwise, just pollutions will create a lot of health issues. There is a clear message or clear direction that electric vehicle is the near future, or which is already happening in the market. I also given an overview about how the overall applications requirements looks like, and then in turn how this is translated. This requirement could be translated to a semiconductors. This finally tells that the high reliable and then high efficient semiconductor is needed in order to optimize the overall power conversion chain. So different technology has to go hands together for a very higher power tracks. Naturally, hydrogen could be one of the directions, and for the city transportations, obviously battery electric powered vehicle could be one of the interesting options. Again, we have looked at long range could be a big discussion topic for the car segments. So long range for the trucks could be addressed by the fuel cell concepts. So for the city, for a radius of 50 kilometer, so naturally we can live with a level 2 AC charger, and then level 3 DC charger. There is no need to go for the higher power charges, which is more than 350 kilowatt. So with this, you can also find a lot of information from our websites. So there are separate pages which has been created for commercial construction and agriculture vehicles, so where you can see what is the overall market trend, and then a few videos and then trainings are available in this following link. And same is applicable for the electric vehicle charging as well. Hope I had given enough ideas about how the market is behaving, what is driving, and what kind of a semiconductor solution is really needed to address these challenges. Now I open up floor for questions.
Participants, if you have any queries, you can ask our resource person. You can unmute yourself or you can ask questions or you can post your questions in the chat box. As there are no questions, I take this opportunity to thank Suresh Sangvelkar for his wonderful session with lot of information related to research as well in industrial domain. I thank Suresh sir for the wonderful session, and it's been a great honor to have you back for our webinars and other sessions, sir.
Thank you for giving me the opportunity to discuss, the challenges in the industry, and then how the industry is working in this direction.
So we have a question. What are the
Yeah.
current research options in fast charging technology? Um,
Oh, just can you? No, I could not hear your voice
so
properly. Can you just repeat
what
the
are the
question?
current what are the current research options in fast charging technologies?
Okay. One could be, the bi-directional, the vehicle to grid is it's just popping up. This could be one of the interesting area, uh, could be looked into it. One is like a vehicle to building, because the same energy can be utilized for your home as well. And this also can be utilized for grid management functions, or it can be also be a good interesting model where you can also sell energy if you have excess energy on your car. So like for example, in the night, you get the energy at pretty damn cheap price. You can store it, and then during a peak time, this also can participate in selling the power. By this way, you can also earn money, and the grid stabilization is also being taken care. This is quite interesting area where people are looking at it.
So we have one more question.
Yeah.
What is the effect of fast charging on grid?
Again, I would say like it's a question that how many fast charges will be coming into practice. This is going to define definitely how the grid system would be. So naturally, we see there are a lot of mitigation techniques already been in place. Like for example, there are huge battery banks being installed in charging stations. So generally, these batteries are charged with the slow charges, and the car batteries would be charged from the charged battery. So by this way, one is like you no need to have a higher power charger. A slow charger is good enough. On the other side, from the battery, you can easily charge your car at a faster rate. So there are different way the industries is looking at, but naturally this is a big concern. Like for example, if you are connecting the city transportation, as I explained, this itself it is going to create a huge imbalance in the power sector. And moreover, if the bigger tracks need several megawatt of power level, and then if many such a tracks is getting connected to the power grid, is of course this create a lot of nuisance on the grid side. So there are a lot of researchers, and then a lot of new product ideas is coming out. One, as I explained, having a buffer storage. So this also can mitigate this. The other way would be, why do we need to go for such a high power charges? Why don't we convert this high power tracks into an fuel based kind of an fuel cell based kind of an technology? So there are different ways people are working around. Again, the vehicle to grid, again, if this becoming in practice, then this also could comes in handy to support this. So there are different ways the industry is looking at it. But it is a serious concern, I would say.
Is so they have asked the continuous question. Is battery replacement effective or fast charging?
Yeah, I think it is like battery swapping technology. This is what I think. If I'm not wrong, the question is related to the difference between the battery swapping and the fast charging, right? Yes, the question is again battery swapping. Again, you need to create a business model to make it successful. Battery swapping is nice, but who would be taking ownership of this battery? And until if you create a business model, then it's fine. I think the battery swapping, I see it's a big talking point in India alone, wherein the other countries are more going in the direction of fast charging, and the fast charging is in the range of 350 kilowatt. Again, the success factor will remains in the direction of how good the automation they do it when they do battery swapping, and do they really need a battery swapping? So these are all the different questions which needs to be answered. But I see even in US and then Europe region, the battery swapping is not at all considered as an option. They go for an fast chargers.
Thank you, sir. Since there are no more questions, I'll again like to thank Suresh sir for his wonderful doubt clearing session. Thank you, sir. We'll meet up again in one more session.
Thank you.
Thank you, sir.
And have a good time.
Thank you.
Yeah.
We'll close.
Thank you, Suresh, sir. Thank you.
Thank you, sir. Thanks for the
Thank you. Bye-bye.
opportunity. Bye-bye.
Thank you, Suresh. Thank you. Bye-bye.